This is the winningest standard bore space big block in NHRA Top Sportsman racing history. And engine builder and racer Sandy Wilkins has got the Wallies to prove it. But times change and cars get faster. So Sandy decided it was time to update this big boy to make sure it keeps winning. So here's what we're going to do. We're going to totally rebuild it, get rid of the carburetor, and add fuel injection. How are we going to do it? That's the fun part. Hang on. When we got to Sandy Wilkins' shops in Mooresville, North Carolina, he had already completed the teardown of the engine and cleaned up all the parts he planned to use again in the rebuild. Believe it or not, this engine has been around since 2011. Sandy actually won an NHRA Top Sportsman Championship with it in a carbureted setup running incredibly consistent 6.30 laps in the quarter mile. It was built to run 125 passes without a rebuild or significant maintenance, and that will still be the plan going forward. It will continue to race in the Top Sportsman class in the NHRA, but this time around with Brown Motorsports. And Top Sportsman, by the way, is the fastest non-professional door car category in the NHRA. Heck, they're even faster than the big money pro stocks. Now, I'm letting you know that because this is a big money engine build we're covering today. In every video I do, even the low buck ones, I always get several people complaining about cost. So if you're one of those people, be ready because you're about to get seriously triggered. This is an expensive engine because it's built to win championships. This is not something you're going to throw into a Fox Body Mustang and go street racing. But that's okay because the Top Sportsman race teams are lined up for a Sandy Wilkins built racing engine. Anyhow, just wanted to warn you because if you're one of those guys that like to complain about cost, that's cool, get it out of your system. But the teams racing these engines sure aren't. In its previous incarnation as a dual carb nitrous motor, Sandy ran about the same times we're going to be running now because in Top Sportsman, you're trying to hit a specific time, no faster, no slower, which is really tough to do, especially when you're running 4.01 seconds in the 8th mile and 6.30 in the quarter mile. The advantage with EFI, though, which is what we're switching to, is its adaptability. Because with carburetors, once you have your settings, they're basically set once you shut the hood, and you got to live with them. With EFI, the computer can actually look out for and monitor the engine and change controls in real time as you're going down the track, which you obviously know. So that makes it, even if you're running the same times, much less likely when you're spraying all that nitrous to wind up with a very expensive blob of aluminum that used to be your race motor. Anyhow, I'll let the man himself, Sandy Wilkins, explain it.
So one of the reasons that we're converting this over to EFI is so that we'll have better control over what's happening in each cylinder. With a carbureted engine, a lot of times you'll have one cylinder robbing fuel and air from another cylinder because of firing order, intake manifold design, header design, etc. With EFI, we can have direct port injection that controls exactly how much fuel goes into each cylinder.
We'll be reusing a lot of components, but there's a lot of new too, like the pistons, rods, valve springs, and other stuff. Wilkins is incredibly meticulous, and everything has already been cleaned and measured, so we're just about ready to go. The block is the same one that's been around since the beginning. It's a Brodix aluminum casting with a stock Chevy big block bore spacing of 4.84 inches. The deck height is taller, however, at 10.7 inches. This aluminum block has also been through the HIP process by Brodix, which is a really cool option that they offer. HIP stands for Hot Isostatic Pressing, which actually increases the density and strength of a casting, which is super helpful if you're talking about aluminum. It's done by putting the casting in an oven that's also a pressure vessel. It's heated up while an inert gas is also pumped in, so the block is under great pressure from all angles. And the result is a stronger material from the atomic level up that you can get from a standard casting. The crankshaft going back into the block is a high-end forging from Callies with 5 inches of stroke. Notice how the leading edges of the counterweights have all been bullnosed to help reduce windage. The crank is also designed to work with a really advanced rear main seal. It's a two-piece design that fits together with scalloped ends so they can lock into each other. It's then held together by a big old O-ring, or maybe you want to call it a rubber band. I can't remember the real term for it. Anyway, it holds it all together, minimal drag, and no leaks. Rich Godfrey runs down the fasteners in the billet steel main caps. In this setup, every main cap uses 4 studs to help secure it to the block, and not just the center 3 mains like usual. The camshaft is a big old chunk of billet steel ground to spec by Comp Cams. Now this is a fat 60 millimeter core to limit deflection because Sandy demands that the valves are opening and closing exactly when he wants them to. And in top sportsman drag racing, when you're trying to run a quarter mile in a target time, no faster and no slower, precision is key. And while I can show you the camshaft, Sandy asked me not to share any of the specs on the grind, which I can respect. But he did give me permission to share some of the general specs. The cam is ground with an LS firing order versus traditional big block. The gross valve lift is over 1 inch for both the intakes and exhausts. And as far as the duration goes, compared to a typical cam for a naturally aspirated engine, the Nitrous cam will have a bit more duration for the intake valves and lots more for the exhausts. Now this is less about making power than it is longevity. The extra duration on the exhaust helps get the heat of combustion out through the exhaust headers. Otherwise, it would heat soak the parts and damage the engine. And then Rich bolts up the belt drive timing set. He also mocks up the #1 piston and connecting rod in the first cylinder so that Sandy can degree in the camshaft. Now, when you are serious about being precise, you use a degree wheel the size of a hula hoop. And then once Sandy has confirmed that the cam is exactly where he wants it and has locked down the adjustable timing gear, he checks the bolt tension with the frequency meter. Now there is no idler to take up slack on this belt drive timing set, so instead he keeps multiple belts on hand that vary in length by just a few fractions of an inch. So now, before we finish installation on the rotating assembly, we need to make our first significant change in preparation for the switchover from carburetors to EFI. That will involve installing a magnet on the cam sprocket in a specific location so that the electronic pickup can see it as it swings by. That's why we had to go to the trouble to go ahead and install everything and then degree in the camshaft. Because Sandy knows where he wants to place the pickup. He's using this billet aluminum Holley unit that allows for a decent range of adjustment, but you'd still like it centered to start. And because he wants it absolutely perfect, Sandy actually went to the trouble to machine a bushing to center the scribe in the bracket.
For this application, I've made a little bushing I can put my scribe in, and then we will put this in the threaded area for the pickup, and I'll just push this in, scribe a little mark on our gear, just that simple, and then now we have a mark on the gear so we'll know where to put the magnet.
Next, it all has to come back apart so that Sandy can drill and tap a hole in the gear for the magnet. And then it can be installed with a dab of Loctite. Here, you can see everything back in place on the engine. Of course, it helps that the cam gear is non-ferrous aluminum. Now, in case you are trying to do something similar yourself and you don't want to go to all that trouble, you can use a steel piece like this that bolts to the front of the cam gear and uses a tab that you can sync off of. You'll just need to use the magnet in the pickup instead. Sandy custom cuts the valve pockets on his pistons himself so that absolutely no compression is wasted. The custom pistons are definitely heavy duty, but they have to be able to withstand a full season of racing with no issues and compete for championships. So that means typically 13 races, and of course you plan to go to the final round every time. So that's at least 3 rounds of qualifying plus 5 rounds of eliminations. And then of course you have to do testing to dial in the suspension, so let's add in another 20 passes to that. So now we're talking at least 124 balls to the wall blast down the track under full nitrous load. And remember, most of the racers in Top Sportsman are working regular jobs during the week and going racing on the weekends. Anyhow, these custom slugs have been sent to Calico Coatings for a heat reflective coating on the dome and an anti-scuffing friction reducer on the skirts. Also, notice the gas ports on the top. These intersect with the top ring groove so that the expansion of gases from combustion travels down these holes and helps push the top ring from the back even more strongly against the cylinder bore. These pistons measure out at 4 inches, 610 thousandths in diameter. So, combined with the 5-inch stroke, that'll make final displacement 668 very vicious cubic inches. The connecting rods are aluminum units from MGP. Lots of people that may not be overly familiar with drag racing engines think that aluminum is favored just to cut rotating weight. But the truth is, with modern steel rod designs, the weight advantage really isn't that significant anymore. Instead, aluminum is a more forgiving material and actually protects the expensive crankshaft if you get into minor detonation or other issues. If you haven't seen a lot of high-end aluminum rods before, the MGPs especially come with unique features. Notice the cap end of the connecting rod has a pin right in the center to secure the bearing. Also, this circular pattern cut into the mating faces is called an integrated locking serration, and it's designed to keep the cap from walking. Once they lock in place with both ends together, the cap screws are bolted down and it's all incredibly secure. Sandy installs the rods on the pistons while Rich goes through for a final cleaning on all the cylinder bores. These pistons use machined aluminum pins that get installed on each end of the pin bores after the wrist pin's in place, and they help support the rings. And the total seal piston rings have been gapped to right at 37 thousandths. The ring pack is sized at 0.43 for the first and second rings and 3 millimeters for the third. And once everything is together, the pistons and rods are ready to be dropped into place. MGP recommends only motor oil for the steel fastener threads because that seems to work best threading into the aluminum body of the connecting rods. So everything is given a final squirt of 50 weight motor oil before the final torque. Rich also checks the side clearance for each specific rod pairing on the crank. The target is between 15 and 20 thousandths of an inch. And then the ARP rod bolts are torqued to 105 foot-pounds. Besides making tons of dependable power, Sandy spends a lot of design energy on making his engines as easy as possible to work on and maintenance between rounds if necessary. Now this is a prime example. The dry sump oil pan comes in 2 segments. The upper segment is for the most part permanently mounted. Here, Sandy marks exactly where the fabricated Moroso pan fits against the block's pan rail. There is no oil pan gasket. Instead, a nice bead of silicone will seal the upper segment of the pan to the block. As you can see, the right side of the pan is pulled as far away from the crank as possible to limit the amount of oil that can bounce back onto the rotating assembly and cause drag. All that extra room also makes it easier to work up in there if you need to pull a piston and rod between rounds, so it's easier to get to everything. The bottom half, or the floor of the oil pan, is meant to come off quickly and easily, so no silicone is used here to seal things up. Instead, it's machined to fit a large rubber O-ring. This section also incorporates a simple windage tray, and beneath that, you can see all the built-in pickups for the dry sump system. As with almost every hardcore race engine, the damper is from ATI. But to help cut rotating weight, both the hub and the shell on this unit are constructed from aluminum. In its original form, this engine had a cam-driven distributor. Now we don't need that anymore, so Sandy fabricated up this plug to seal off the hole. The lifters are Jessel Sportsman tie bar units. For extra durability, they've been given a super hard DLC coating. But to help get a bigger roller wheel in there so it can handle crazy aggressive camshaft ramp speeds, the lifter boards have been honed oversized from the stock size of 843 thousandths all the way up to 937 thousandths of an inch. And to help straighten out the push rods, some of the lifters utilize cups that are offset by 180 thousandths of an inch. Sandy also has his own multi-layer steel head gaskets made by Cometic to suit his requirements. The biggest reason for the custom gaskets is revised coolant portholes sized specifically to be optimized for drag racing. Now, generally speaking, it's a small thing, but that's Sandy's approach to every component on his race engine builds. No detail is too small to consider when you're searching for every advantage. Like the block, the cylinder heads are also from Brodix. These castings actually have a pretty extreme 12-degree intake valve angle, especially when you compare it to stock big block, which is at 26 degrees. This is based around the very successful Big Chief cylinder head with its asymmetrical ports, but it has been heavily modified. Notice that we're not showing you the combustion chambers in this video, which is at Sandy's request, and I'm definitely going to respect that. But I do know and can share with you that the valves are sized at 2 inches 520 thousandths for the intakes and 1 inch 860 thousandths for the exhausts. Both the intakes and exhausts are titanium, and at least the exhausts have a protective coating. Out of the box, which means before Sandy did any custom enhancement work, these castings can flow a massive 571 CFM at 900 thousandths intake lift. And what they're capable of flowing now, well, only Sandy knows. Another cool feature to make a racer's life easier are these head savers. Now these are basically washers that are machined to insert into the head so that they can't fall out. So no more listening to a washer fall into the engine bay and hoping you hear it hit the ground. Sandy has also rerouted water flow through the cylinder heads. The main purpose is to make the intake manifold dry. It helps the air charge remain cooler going into the engine because there's no hot coolant in the intake manifold at all. Notice how the coolant port in the intake face is filled with epoxy. Instead, the coolant exits the heads through an AN fitting bung welded into the front of each cylinder head, which you can see. The head studs are pulled to 70 pounds each, but there are a few that are just a bit tricky. There are no compromises allowed when it comes to laying in ports in these cylinder heads because they have to flow the absolute maximum of air and fuel. So a few of the head studs have to be reached through the intake ports. Here you can see the hole in the floor of the intake port. Now it's just for access. The stud doesn't extend up into the port. There's also a hole in the top of the port so that you can use a ratchet extension to reach through the intake ports and secure the nut on the stud. Since almost all flow at this point is across the roof of the port, the little bit of unevenness across the floor doesn't really hurt anything. But flow across the roof of the intake ports is really important. Once all the head studs are torqued down, Sandy installs the rocker arm bar. Now, as you can see here, he's already welded on plugs and ground them to the correct shape to perfectly match the profile of the top of the intake ports. They're even O-ringed to eliminate any vacuum leaks. And once the rocker stand is bolted down, well, they aren't going anywhere. And that rocker stand, by the way, it's machined from steel and secured in place with 12 bolts to provide the most stable platform possible for the rocker arms. A lot of effort went into maximizing the Valvetrain to be able to run super high RPMs for an engine of this size. We're talking shifts at 7,600 RPM and a red line of 8,200. The valve springs are all from PSI Spring. They are a triple spring setup to be able to generate lots of spring pressure and valve control. But unfortunately, I can't get into specifics in terms of spring pressures. The retainers are manufactured by Del West and machined from titanium. They've been given a moly coating to prevent galling, and the installed height is right at 2 inches 200 thousandths. Sandy moved on to this oil line. There's a port cut through the valve cover rail at the back of the head, and this drains oil to the pan, as you can see, so it bypasses both the camshaft and the crank. Here, you can see the hole in the back of the head that leads to the AN fitting and the drain line. Under acceleration, all the oil is headed straight back here anyway. Like all big block Chevys, the intake and exhaust push rods are 2 different lengths. To greatly reduce the possibility of somebody screwing up and putting a push rod in the wrong position, Sandy uses machinist die to mark the intakes with a bright blue and the exhaust push rods with red. It's a simple solution that can potentially pay off big dividends just by keeping somebody from making a mistake. And now we have everything together for the Valvetrain. Those big push rods, by the way, aren't just different in length. The intakes are 10 inches 875 thousandths long and a ½ inch in diameter, while the exhausts are 11 inches 100 thousandths long and also just a bit bigger in diameter at 9/16 of an inch. The rocker arms have a machined steel body and obviously are full roller. The intake rockers have a ratio of 1.9 to 1 and have 2 different offset styles to help straighten up the push rod angles with the large intake ports. The exhausts are slightly less aggressive at 1.85 to 1. Once all the rockers are bolted down, Sandy sets the lash at 8 thousandths of an inch cold. With the aluminum block and cylinder heads, once the engine is warm, they will expand much more than the steel push rods, and so the lash will open up appropriately. And here you can see how the intake ports are given priority in this design in order to flow absolutely as much air and fuel as possible, and just how hard you have to work to fit the big push rods in around them. Now, let's move on to the intake setup. On the right is the old carbureted intake, and on the left is the new fuel-injected version built for Wilkins racing engines. The old setup uses 2 big Dominator-sized 4-barrel carbs that are approximately 1,450 CFM each. And those 2 carbs are basically centered over the plenum, but not specific to the intake runners. But the new fuel-injected setup uses 8 individual throttle bodies, with each one directly over an intake runner to maximize port velocity. Each throttle body has a diameter of 2.375 inches. Both the old and the new intakes utilize nitrous as a power adder, but the advanced controls of the EFI system allows for 3 stages of nitrous precisely controlled through the Fuel Tech ECU in a dry fogger setup. Now, even though it's a fabricated intake manifold, the runners are thick enough to be hand-ported to perfectly match the intake ports in the cylinder heads. Here, Sandy glues on the intake gasket. And since the ports are finished by hand, he takes a moment to clean up any overlap with a sharp razor blade. Then, the side of the gasket mating to the cylinder head is given a light coat of grease. This is used because it helps ensure that the gasket won't stick to the head and can be reused if you have to pull the intake manifold. A small bead of silicone seals the China rails, and the intake is ready to be carefully set in place. Here, you can see the straight shot from the intake plenum right down into the cylinder head's intake ports. The three-stage Nitrous system can be pretty complex, but this setup from Switzer Dynamics is super sanitary with all three stages plumbed to a single nozzle, so tuning adjustments should be pretty straightforward. Sandy says that on a 6.30 second run in the quarter mile, the engine will typically run 26, 28, and 30 jets to start. Now that's at least 700 horsepower worth of nitrous. The intake assembly is also designed to be as modular as possible. The fuel filter is below, and that's a fuel pressure regulator up top. So if you have to pull the intake, you just have to uncouple the fuel line at a single point. The plenum top shouldn't have to come off at the racetrack, so it's sealed with a simple bead of silicone. But the bolts used here are pretty interesting though, because they're actually made from aluminum. This is actually a safety feature because Sandy says if something goes wrong, this engine can backfire bigger than the burst plate can handle. So the aluminum bolts are designed to break away and release pressure through that big top plate in order to save the engine from worse damage. With the butterflies open, you can imagine how those 8 2.375 inch diameter throttle bodies can flow a Category 5 hurricane worth of air when the engine calls for it. Now we're down to the finishing touches. Sandy installs a magnetic pickup for the cam location sensor. Zach Thomas test fits a blank engine mounting plate. He still needs to trim the plate for the AN fitting water exits at the front of the cylinder heads. Now when everything is right, the motor plate will be O-ring for the water passages through the front of the block, so it won't require any silicone to seal up. And here's the completed front drive setup. On the left, you can see the pickup for the crank trigger, which has been bolted in front of the harmonic damper. Now on the right is the belt drive for the 5-stage external oil pump that goes with the dry sump system. And what at first glance may look like a water pump is not. The water pump will actually be an electric unit and mounted remotely. You can see where the water lines screw into the black mounting system with AN fittings. The billet aluminum piece that's anodized red is actually the fuel pump from Waterman Racing. It's driven by a shaft off the front of the cam drive and is capable of providing tons of race fuel at high pressure to the injectors very reliably. You can see the drive shaft right here. On the dry sump side, you can see how the oil lines from the dry sump pan are super tight and tucked out of the way. Sandy says the system is efficient enough that there's no need for a separate vacuum pump like you normally see in drag racing applications. And here's the completed engine ready to rock and roll. It's obviously a monster. Normally at this point, we head off to the engine dyno and bust off a few pulls. But that's not a common practice in high-end drag racing where tuning is done on the chassis dyno or even at the racetrack. So this big 668 bad boy went straight to Brown Motorsports for installation in the race car. As I mentioned earlier, this engine is purpose-built to win championships in top sportsman drag racing. And what's incredible about that to me is that it's designed to go all season long and win that championship without a rebuild. And we're even including things that a lot of people consider consumables like valves and valve springs. On top of that, it turns out 1,300 horsepower and it's safe to on just race fuel, and then you throw in the nitrous for another 700 horsepower to make a grand total of an easy $2,000. And of course, like I said, that's the safe tune. If you want this engine in a different application or to do something else, Sandy can easily tune it up to make a whole lot more than that. Anyhow, thanks for watching. I know very few of us are ever going to need an engine like this, but I think it's always fun to see how these top level race engine builds go together. If you enjoyed this, please leave a like and maybe a comment. Let us know what surprised you about this build. And we'll be back next time for even more great engine builds. Thanks again.